Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Dr. Tanvir Hussain, who is an associate professor in materials engineering and a program director for aerospace engineering at the University of Nottingham. Hi Tanvir, how are you doing?
I'm doing all right. Thank you very much. How are you doing?
I am super excited to speak with you and understand your science.
Oh, me too here. Can't wait.
Let's start. Let's start by understanding your scientific journey so far. So, how did you end up in your current research field?
Um, I was doing my master's at the time and I was interested in laser actually. So I was about to start a master's project on laser, but then that particular supervisor left the university and went on taking a pro vice chancellor position somewhere else. So I ended up with someone who was talking about something called cold spray. And I didn't know anything about cold spray at the time, and that was 15 years ago. It was basically it's a wonderful process where you have got a small metal particle or a ceramic particle and you accelerate to supersonic speed, and when it hits the surface it deforms and stick to each other, and that's how you build a layer without having any heat. So I've gone from a heat based process to a complete not heat based process, and from that point on, I just did a PhD in cold spray, then carried on doing postdocs, being an academic, and then the journey for thermal and cold spray continued.
Aha, interesting. Cold spray. Wow. That's
So,
that's really cool.
so the proper name is cold gas dynamic spray. It's essentially a high, when things deform at very, very fast rate. So you don't need to add any heat to it. It's just because something is traveling so fast. If you think of a bullet, so if you think of a bullet, it's traveling very fast, and if it hits another metal, it will deform and stick to each other. So
So cool.
metals can behave differently at a very high sort of rate of deformation, and so you don't need it to melt anything. It just bonds. It just sticks together.
It's just the speed. You control the
Yeah.
speed, accelerate it so fast that
Yeah.
it just changes its
Yep. The
structure or
properties.
something.
Yes.
That is so cool. It's good that you went to this, and it's good that your supervisor or whoever it was went to it.
Yeah. So I ended up in my field just in one sense by chance, rather than planning it well and knowing that I really want to do X or Y.
Right, that makes sense. That's so cool. So, your current research, let's talk a bit about that. So, where does it fit in this big picture of materials and nanoscience? Which piece of the puzzle are you?
So a lot of the research I do are kind of interdisciplinary. So in my team, I have, if you think of engineering discipline wise, I have researchers from chemical engineering, from material science, from materials engineering, mechanical engineering, manufacturing engineering. So they all come from slightly different background. But the subdiscipline I would say I fall in is surface and coatings and interface. So that's the bit we are active in. And if you gotta distill it down to processes, then I would class myself in surface engineering processes.
Uh-huh. Okay. So, it's surfaces, interfaces, those kinds of things.
Yeah.
Okay, that makes
So,
sense.
so if I could add a little bit, so modification of surface could be something very simple, like a paint, what you have got on the wall. So someone using a polymer paint to paint your wall, but the sort of things we work with are high value manufacturing. So these are the sort of high end of the surfaces, which are very expensive equipment, and these are very safety critical components, if that makes sense. That's so, although broadly it's all surface and coatings, but there is an element within that one which is for high value manufacturing things.
Uh-huh. Okay, that's interesting. So it sounds to me that you do a lot of interesting experiments. So, and you have done a lot of interesting experiments, hopefully in the past. So if you have to pick one that you're proud of or the most quirky one, could you pick one experiment or research project out and explain it to us in simple words, the section we call In Other Words?
It's very hard to pick
I
one
know.
particular project out of all the things I've done in 15 years.
Yeah.
But one of the challenging ones I've done in last 2 years was, so you all know about the graphene stuff, and everyone is so excited about graphene. It's this wonder material, came out of University of Manchester, and there's a Nobel Prize on it. A lot of the work we do is with cheap, poor man's graphene nanoplatelets. So it's not single layer, it's 4 or 5 atomic layer thick, and
Mhm.
it's very cheap to buy. So
Okay.
we then try to incorporate those with ceramics or other oxides
Mhm.
into coatings. And
Okay.
we have got a patent on it. And the benefit of having something wonderful like graphene nanoplatelet or multilayer graphene is the performance can improve by an order or two of magnitude. So imagine a simple aluminum oxide, which is very hard wearing as a coating. You can use it on drill bits. It's widely used in aerospace engines. But if you can then make a coating with this alumina with graphene nanoplatelet dispersed uniformly, the wear resistance could improve by 2 orders of magnitude. So something very cheap, something simple, but you can get wonderful sort of improvement. So that's probably one of my sort of highlight. It was challenging. It was hard work. We failed many, many times because graphene doesn't like high temperature. So when we tried to include it, it just wouldn't go into just go into carbon dioxide. So
But that is so cool. So this big hype of graphene is real to some extent.
So I think because the community is quite diverse, so there are lots of people working on electronics and very, very pure form of things, whereas we have chosen, and also a lot of other polymer composite people who are trying to include multi-layered cheap graphene into car tire or plain structures for polymer composites to improve properties. So I think
Mhm.
when it comes to industrial application, you'll probably see multi-layered graphene as an application before you see all of those very, very expensive, fancy applications.
Mhm. I like that how I liked how you honest you were that you mentioned at the beginning at the start itself that we don't work with graphene. It's a few layers of carbon atoms, so we call it a nanoplatelet.
Yes,
It's not
yes.
graphene.
Yeah. Because I think it means different things to different people. So for a pure chemist, graphene is single layer, or a
Yeah,
pure physicist. Anything more than one layer, they would say it's not graphene anymore.
yeah.
So it's how you define it. But if you think of graphite, graphite has been used in lots of applications for decades. So
Hmm.
even in plane engine seals, we use graphite reinforced stuff. It's a lubricant. It's cheap. It works quite well.
Hmm. But it didn't have the Nobel Prize tag to it.
No.
That tells. So well, that's wonderful. That's an interesting project, and that is. Do you know if that technology is being implemented, or can you not talk about it?
um, there are lots of people working with it, and I think these are probably, if you think of the technology readiness level, some of your audience probably will be familiar with. There is 1 when there's a concept and 9 when there's an industrial application. I would class it's around 5 or 6 at the moment. So there are industrial companies who are putting things in their prototypes and measuring values and
Okay,
performance.
okay, sounds cool. So let's go get out of the lab and let's go more towards the lecture hall. So, do you teach? And if you do, what other courses do you teach?
Um, I do teach in British universities, in Russell Group's type universities. All academics are contracted to teach 50% of their time, and
Ah,
other 50% is research. Yeah,
oh,
so
okay.
that's got a lot of teaching to do. But
Right.
but because I do the aerospace program, I don't do a lot of the teaching now. But the modules I still teach are aerospace materials to year 1 students, around 130 students,
Mm-hmm.
and then I teach surface engineering and aerospace materials processing to year 3 and 4, which are smaller classes.
Right. Okay. And do you like it? Do you enjoy it?
It's rewarding. One of the perks of being an academic is you get to train the next generation of scientists and engineers. And I think it's as rewarding as research. And
Mhm.
sometimes there is obviously a tension between research and teaching for academics, but being able to train the next generation is the most rewarding thing you could do in a career. So yeah,
Mhm.
I enjoy it. It is demanding, it's hard, and sometimes when you're thrown into lecturing large students, I used to lecture to 300 students in one lecture room, so which can be quite hard because
Yeah,
the way you can interact with 30 students is very different when you have got 300 students. But
true.
overall, I enjoyed it. I delivered a lecture for 2 hours today to 130 students, and I
Oh
think
my
students
God.
enjoyed it.
Ah, that's wonderful. That's really nice to hear. And it's also beneficial for the students if they get lectured by people who actually enjoy it and not just do it for the sake of it.
Yeah.
Right?
Well, I think you got to understand one thing is universities are here to train the next generation. So teaching is at the core of what we do. And and now when I look back, when I started teaching 10 years ago, it was it was hard when you're thrown in front of 300 students and lecture something which you may know very well, but how do you transfer what's in your head to someone explained in a way they will understand? It's a skill I'm still learning.
You're polishing that skill all the
Yeah.
time. With every lecture, you get better.
Yep. Hope so. Hope so.
Okay, let's talk a bit about your research experience. I hope your research experience has been wonderful so far and will continue to do so in the future. However, if you had three wishes to improve it, what would you ask for? And I'm not promising anything here.
Um, if you could ask for anything, one of the things, so I would class myself as a mid-career academic. So I've got a well-established group of 15 researchers doing wonderful things, but we still struggling in terms of research-wise, having equal opportunity and access for everyone in
Mm-hmm.
terms of research. So this the equality, diversity, and inclusion is a big thing, and
Mm-hmm.
that means equitable funding or equitable opportunities, and that's still one of my core wishes, that if we get that, then the work culture would be much better. And that brings me to my next one. Wellcome Trust recently published a new report on working cultures and research cultures, and I think there are lots of great people around in the research field, but our culture is not very productive at the moment because it's feeding competition as opposed to collaboration. So we gotta find a way where we harness the power of collaboration and just build each other up rather than fighting within the within the small domain.
Right.
Um, how many wishes did I tell you? Two.
Two.
So the third one possibly is along the line of in the UK, we have been pushed more towards doing applied science and applied research because impact has been quite a big thing. As an engineer, that's quite rewarding, but that also means it comes at a cost of lack of funding for blue sky, crazy ideas, high risk ones.
Mm-hmm.
So if we could get more funding for those high risk blue ideas, I think that would be a wonderful thing for our research field.
Mm-hmm. Okay, interesting. That makes sense. I really liked the second part, the second one that you said, that more work together towards something big rather than doing this. Is it the frog thingy? The frog experiment, like pulling each other?
Yeah. Well,
Yeah.
the thing about academia is if you say, I think when everyone starts their PhD, they all start from a very collaborative mindset and they all want to collaborate and help and support each other. But the way we have done a funnel system from going from master's to PhD to postdoc to a permanent position, then to tenure, is we are narrowing things down so much. There is just not enough opportunities and enough options available for all these brilliant scientists. And as a consequence, what you end up doing is uh, not rewarding collaboration. So there is lots of collaboration happening between big research group PIs
Mm-hmm.
within different groups all over the world. But I would like to see a lot more collegiate environment in research.
Uh-huh. Okay. Yeah, that makes sense. That makes sense. That would be great.
Yeah, I mean, rather than imagine what a world would it be if we could just share all of our ideas with each other and say, I don't have time to do it, take it and do it.
Yeah, absolutely. Rather than keeping the idea with you in your brain and being like, oh yeah, I'm gonna work on it 2 years down the line.
And there is something else comes up and then it dies or it disappears.
Exactly. Just share, just communicate, just collaborate.
Yeah,
Uh,
I think there are lots of other disciplines a lot more collaborative than probably the sort of disciplines I am in, which is super competitive. Well, nanomaterials, nano side is usually super competitive, as you know, because
Right.
there is always a race going on who could do something for the first time.
Yeah, absolutely. And also from the engineering point of view, the IP, I guess, is quite a big thing as well.
Yeah.
The yeah.
So a lot of the industry funded projects we can't really talk about. For example, there is always an NDA or other things in place, which I
Right.
understand if there is a money making element of it, we got to respect that.
Mm-hmm.
Uh, but even working within that framework, I think we could still be more collaborative and support each other.
Mm-hmm. Yeah, that makes sense. Well, I hope we are working towards it. I hope the scientific community is working towards making all the three wishes happen. Also, the funding one, I think that's also
Yeah,
very important. Very, very
yeah.
important.
And I think so. I do worry about the early career researchers because I was things are a lot more different now compared to when I was, and things are getting harder and harder.
You see that? You feel
Yeah,
that?
for early career researchers, yes. I think the sort of pressure they're under, I don't think we're under that sort of pressure.
Mm-hmm.
So if that trend continues, I could see the early career researchers going through even more intense pressure in next 10 years,
Okay.
which cannot be healthy for a field or STEM in
No,
general.
no, it's not. It's not. And then we also, I mean, I understand that the pressures are building. They're also building for kids as well. Like from kindergarten onwards, there is so much that a human being has to consume. But then we have to train them properly. We have to create environments where they thrive uh,
Yeah,
quite well. So, well, I hope we are working towards it. And you can
yeah,
tell us more about it 5 or 10 years down the line, or two
hopefully.
years down the line. Be like, ah, yeah, the change is coming. We are collaborating more.
Yes, we are hopeful, we are optimistic. I think we're gonna change the reward. We're gonna reward um, collaboration over competition.
Collaboration over competition. That should be like the motto for everyone, just as a reminder for researchers. Okay, wonderful. Let's move on to the future. Speaking of the future, what are you most looking forward to in the next 3 months?
In terms of research wise, we have developed a hardware which essentially can sit in front of a small rocket engine. So,
Mm-hmm.
so that spray torch is called high velocity oxyfuel. So
Okay.
when a rocket engine takes flight, exactly the same sort of things happens in the same torch. And we have been working on it for the last 2 years in a way that you could inject nanoparticles in a liquid as
Mm-hmm.
well as some nanoparticles dry, and they can all combine in a supersonic flame,
Okay.
and it could turn into this wonderful material and coatings which has never been possible. So that's what we are really looking forward to, and that when we actually get to combine magic of A and B together and get a material which outperforms everything else.
Okay. What is the material supposed to do? Can you talk about it or?
So lots of things you could do. So think, as an example, think of nanocomposites.
Mm-hmm.
So you could add a very small amount of, let's say, boron nitride or
Mm-hmm.
hexagonal boron nitride into a oxide, and combining hexagonal boron nitride with an oxide, you could get unlock some wonderful properties which is not possible for boron nitride to have individually or oxide to have individually.
Mm-hmm.
So that's sort of things.
That sounds cool. Well, looking forward to that. Looking forward to reading a paper about it and following your Twitter feed for the
Oh
same.
yes,
Uh,
thank you.
and before we let you go, what we want to understand from you is what is the research field of materials or nanoscience working towards? What are the big challenges that the scientists are trying to solve or go around?
Um, every research field reinvents itself every X number of years. So if you think of 20 years ago, anything to do with nano was fashionable. It was exciting. There was a lot of funding in nanoscience at the time.
Right.
Things have changed slightly because it's no, a lot of people are doing it, so there's a lot more participants there, which is great for a field. But the size of funding pot hasn't increased at the same sort of rate. So as a
Mm-hmm.
consequence, there's a lot more competition to be able to do the science you want to do. So that's probably one of the sort of the funding resources is a big challenge. So in the past, 20 years ago, there used to be dedicated funding for nanoscience, whereas those funding posts are now being swallowed under big umbrellas of advanced materials as opposed to just nanoscience. Um,
Right.
and I guess I've mentioned the research culture thing, and we're doing individually, group wise, lots of useful stuff, but we got to be learn to how to collaborate better. And that collaboration goes all the way from far East Asia to North America and Europe and everyone together. Rather
Mm-hmm.
than trying to develop things individually, how could we develop a model where we can develop something, someone else in Asia could develop something else, and someone else in Canada could develop something else, and you bring all of this together. Nowadays, I mean, we are recording a podcast over Skype,
Mm-hmm.
so in, so our collaboration really haven't gone to that sort of stage. We are still very much our group, our sort of university, very much local orientated thinking.
Right, right. So more across
Yeah.
continent, collaborative, as you said several times, more collaboration over competition, right? That's what.
Yeah, it's particularly important for British scientists because of the Brexit stuff.
Oh,
Because
we're gonna
you
go
could,
there.
yeah. So, but you could imagine that a lot of the research we could do is because of the European funding, and what we're going through this year, it's an uncertainty, and that's again when it comes to the collaboration, it's top of our agenda. How do we keep collaborating with all the other countries and the great scientists we have been collaborating for years?
Right, right. That makes sense. Well, I hope that the challenges, the fog clears up, at least for the scientific community. The other political stuff and trade stuff is also important, but what is very important, I feel, is the scientific research activities. The fog around those
Yeah,
policies gets cleared up soon.
yeah.
Uh,
I
also
mean,
for the also for the people who are coming in or going out of the UK, the researchers who are coming in, like the international researchers, the diverse researchers bringing their own experience. It's so uncertain at the moment.
it is a tricky time, and I think the message is nothing really has changed, but people's perception has changed. That's
Mhm.
what worries me. So whenever we used to advertise and we used to get an enormous number of applicants from all over the world and Europe and things. But
Mhm.
now we are starting to see a bit of change. So in real life, nothing really has changed, but it's the perception. So we got to
Right.
be mindful that you can't do science in isolation. It's just never going to happen. You
No,
have to be able to work with people and develop things collaboratively.
true. That makes sense. I think that's a very nice note to end the broadcast on collaboration. Collaborate as much as possible, as often as possible. So, thank you very much, Tanvi, for taking the time for speaking with us, and we look forward to having you on Real Scientist Nano.
Oh, thank you very much for having me on your podcast and also giving me the opportunity to take you to the handle. Thank you.
Wonderful. Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.